again to this lecture number 24. We'll first recap the last lecture, and in the last lecture we looked at the microstructure evolution in a eutectic phase diagram. Of composition C less than CE. Okay. So, we first looked at the composition in which we formed a single phase alpha like this. So, this was C1 composition, and then we looked at composition C2, which was between C alpha E and C alpha let us say 0 at lower temperatures. So, what we had there was we had these grains of alpha. So, this is alpha, and in between we had these precipitates of beta phase. So, this is beta phase, and which were present in the matrix of alpha. So, the composition of alpha was C alpha was lower than C2, and C beta was higher than, way higher than C2, and phase fractions can be found using lever rule. And then we looked at composition C3, which we were looking at, is in which you have alpha phase. So, you have alpha phase. Within this you had these sorry, let me draw it differently. So, we had these alpha grains. These were alpha grains, and between these alpha we had this eutectic phase. So, this is eutectic. So, let us say this white, in this I think it is easier to draw the white one, but this is pro-eutectic alpha, and what you have here is alpha plus beta eutectic. So, this is where we were. So, we will continue our discussion on this. So, we drew a microstructure for phase diagram like this. And we were in this region. So, this was C3. So, at this point, so when you draw the phase diagram completely, this is, let us say, the phase diagram. I am sorry. Okay. So, this is the composition CE, this is the composition C alpha, this is the composition C beta at eutectic temperature, and then you have C alpha, C beta. So, when you are at this point, the compositions of alpha and beta are given as C alpha. Let us say, I can't remember what was the point. Let us see what point it was. It was point E, okay, at point E. So, when you are at point E, this is the point E, let us say, below the eutectic temperature. So, at this point E, you have alpha of composition C alpha, let us say, which is almost similar to eutectic composition, and then liquid, and then alpha plus beta mixture, which is eutectic mixture of composition So you can have two ways of describing it. You can say the alpha of composition C alpha and eutectic of composition CE, or if you just want to describe in alpha and beta, then you can say alpha of composition C alpha and beta of composition C beta, which is this one. Okay. So it is necessary to understand this difference, because otherwise it will create confusion in understanding what you get here. So I'll come back to this later, but at point E, the microstructure that you get in the previous picture, it's a mixture of alpha plus beta. Okay. So this alpha plus beta can be described in two ways. So first way could be it is alpha plus eutectic. Okay, this eutectic, it is alpha plus beta, or you can simply say it is alpha plus beta, which is also fine. But then the distinction is here alpha is present in two different forms. Although the alpha of composition of alpha is same, composition of alpha in both eutectic as well as in pro-eutectic phase is same as C alpha. The form in which alpha, in this image, the alpha pro-eutectic alpha is present in this form of these grains, whereas in the form of eutectic it is present in the form of these plates. Both of them have similar composition, it's just that their morphology is different, whereas beta is present only in the form of plates. So this alpha is pro-eutectic alpha and this is eutectic alpha. So the choice is generally of the reader, whether he or she would like to present it as pro-eutectic alpha plus eutectic alpha and beta, or total alpha and total beta. So how do you find the proportions of these alpha and beta, pro-eutectic alpha and alpha plus beta, or alpha plus beta? We'll come to that later on. Now finally, let's discuss the microstructure evolution of case 4, which is of composition C4, which is same as CE. So now we are looking at eutectic composition. In this case, the phase diagram, so let us just draw the phase diagram corresponding to the eutectic region. So we have liquid plus alpha, liquid plus beta, and this is of composition CE, and this transforms at various points. So now let us look at the transformation at various points. At this point, it is 100% liquid of composition CE. Okay. Just before the eutectic temperature, let us say point B, which is, let's say, TE plus, just before the eutectic temperature, it is in 100% liquid form of composition. Just below the eutectic temperature, at the eutectic temperature, it undergoes a eutectic reaction. At TE, liquid of composition CE, liquid of composition CE dissociates into two phases, alpha of composition C alpha E eutectic plus beta of composition C beta E. So at TE minus, what you will see, which is at point C, okay, at C, what we will see is that a mixture of only alpha and beta. So the microstructure would look like this. So you will have these grains of eutectic. So these are, so let me like this. So this will be alpha plus beta eutectic mixture. It is 100% eutectic, consisting of alpha and beta. Alpha of composition C alpha E and beta of composition C alpha C beta E. The alpha and beta proportions can be found out by applying lever rule. So we will do the exercise of, so this is C alpha E, this is C beta E, and this is C E. The proportions can be found by applying lever rule. So this is how the microstructure evolves. Microstructure, so when you have composition either on the hypo or hypereutectic side less than the solid solubility of B in A or A in B, you form a single phase alpha. You can have beta if you are on the B side. When the composition is higher than the solid solubility of B in A at room temperature but lower than the solid solubility of B in A at eutectic temperature, which is typically higher, then you have grains of alpha with small precipitates of beta present in the grains of alpha, where alpha composition is typically lower than the alloy composition and beta composition is significantly higher than the alloy composition, but the proportion of beta is significantly lower. In the third case, what you have is you are in the, so let's before we go to third case, we go to case 4. In this case, we are at the eutectic composition where liquid of composition Ce transforms directly into a mixture of alpha and beta, and alpha and beta, since they form all of a sudden, liquid has to convert into alpha and beta together. It tends to form in a ordered fashion. So the way it forms is that you have these colonies of alpha and beta growing parallelly like this. So this is alpha, so this is beta, let's say this is alpha, this is beta, this is alpha. So let's, for the sake of color coding, let's say this is of this color, whereas beta is of this color. Okay. What happens is that we know that alpha is rich in A and beta is rich in B. So as a result, since alpha has formed from liquid and it is rich in A, the B atoms have to migrate to this side. So B atoms migrate to this side, whereas beta phase being rich in B, the A atoms migrate from beta to alpha. These are A atoms. So A atoms migrate from beta to form beta, so that they go towards alpha, whereas B atoms are shifted towards beta so that they form beta. So that is, and since it happens together, both of them grow together, and they grow together in the form of parallel plates typically, which are called as lamellas. So these are lamellas or parallel plates of alpha and beta, which grow together through solute partitioning. Okay. So this is how the microstructure of a eutectic would typically look like: parallel plates of alpha and beta. The composition of alpha would be C alpha, composition of beta would be C beta E, but the overall composition of alpha and beta would be C E. We will come to the alloy fractions, phase fractions a little while later. And for the composition which is between the solid solubility of B in A and the eutectic composition, you have a microstructure like this, in which you form a pro-eutectic alpha, which is this phase. So this is the gray phase, pro-eutectic alpha. And whatever liquid is remaining just above the eutectic converts into the eutectic alpha and beta mixture, where alpha beta phase is the red phase and alpha phase is the light colored phase, and so the microstructure looks like this. So I will show you the real microstructures in a little while before we finish, but let's finish the composition analysis and phase fraction analysis of eutectic phase diagram. So I hope you understand what we have done at this point in terms of microstructure evolution. So now let's look at changes in the phase compositions and fractions. So let us first begin with eutectic composition itself. Okay. So this is percentage B, this is CE. Okay. So at CE, so this is eutectic temperature, just above, so for C is equal to CE, okay, alloy composition is CE. So just above TE we have 100% liquid of composition CE, just below TE we have mixture of alpha and beta, alpha of composition C alpha E and beta of composition C beta E, C alpha E and beta of composition C beta E. So this is at this point. So first we are looking at this point A, and now we are looking at B. Okay. So we draw the tie line. Okay, and percentage of alpha is nothing but C beta E minus CE divided by C beta E minus C alpha E, okay, into 100. Similarly, percentage beta will be equal to 100 minus percentage alpha, or CE minus C alpha E divided by C beta E minus C alpha E into 100. So this is how you determine the proportion of alpha and beta phase in the eutectic when you have 100% eutectic mixture. Now what happens when situation is different, when you have what happens for composition which is less than CE in the hypoeutectic region. Now analysis which we are doing for hypoeutectic region is valid for hypereutectic region as well. So we will not do that in here. So we have, again we draw the phase diagram. Now we are at a composition which is this composition, which is C naught. Okay. So this is the composition C naught, which is so this region is called as hypoeutectic region. Okay. So just above this temperature, so we first look at the temperatures. So this is TE. So we look at point A, which is equal to TE plus, and we look at point B, which is at TE minus, just below TE and just above TE. So at A, okay, just what we have is we have liquid of composition. So if we draw the tie line, so we have liquid of composition CE. So this is the point CE, this is the point C alpha E, and this is the point C beta E. Liquid of composition CE in equilibrium with alpha of composition C alpha E. So this is pro-eutectic alpha. Okay. So what is percentage liquid at this point? Percentage liquid is or fraction, let's say fraction of liquid, okay, FL. So FL is nothing but C naught minus C alpha E divided by C E minus C alpha E. This is the FL, and F alpha is nothing but C E minus C naught divided by C E minus C alpha E. These are the fractions of two phases. Now this liquid will transform into, so this is fraction of pro-eutectic alpha, pro-eutectic alpha. Now the moment you come to point B, you have two options. One, either you describe the microstructure as alpha or beta, or you describe the microstructure as pro-eutectic alpha plus eutectic. So when you want to do as pro-eutectic, when you want to do just as alpha and beta, in that case when you draw the tie line, you look at the intersection of tie line with the alpha and beta solvers. So this point, which is same as C alpha E and C beta, so at point B, which is just below eutectic temperature, alpha is of composition C alpha E and beta is of composition C beta E. So fraction of alpha is same is C beta E minus C naught divided by C beta E minus C alpha E, and fraction of beta is equal to C naught minus C alpha E divided by C beta E minus C alpha E. However, if you want to now represent the microstructure in this case, then fraction of pro-eutectic alpha is now, in this case, instead of considering now you are considering pro-eutectic phase alpha and eutectic phase. So if you want to consider the eutectic phase, you need to consider this as a boundary of tie line. So when you draw a tie line now, the tie line is from here to here, not from alpha to beta, it is from alpha to eutectic. So then fraction of, in this case, your alpha is of composition C alpha E and eutectic is of composition C E. Okay. So FPE, the pro-eutectic alpha, F alpha PE is equal to CE minus C naught divided by CE minus C alpha E. Okay. And F eutectic is nothing but C naught minus C alpha E divided by C E minus C alpha E. And if you notice, what we have done for point A is same as for point B if you consider pro-eutectic alpha and eutectic. Basically, whatever the liquid was present earlier, that is converted into eutectic. So these two are same. The percentage liquid that is calculated here at point A is same as percentage eutectic that is calculated at point B if you just consider liquid. However, if you consider alpha and beta phases separately, then their compositions as well as fractions are different. So now you can also calculate from this. This is the amount of pro-eutectic alpha, this is the amount of eutectic. You can calculate what is the amount of alpha in the eutectic. So amount of alpha in the eutectic would be amount of total alpha minus, so amount of total alpha in alloy minus pro-eutectic alpha. So total alpha in the alloy is given as, let's say, which is basically this F alpha, so which is F alpha minus F alpha PE. This is how you determine, and this you can also determine from just by doing the, and this should work out to be same as so this alpha in the eutectic will be same as C beta eutectic minus CE divided by C beta eutectic minus C alpha eutectic. So this should be same as this. So if you subtract F alpha PE, if you subtract F alpha PE from F alpha, so which is basically, you can do the maths, so basically C beta E minus C naught divided by C beta E minus C alpha E, C beta E minus C alpha E minus of CE minus C naught, CE minus C naught divided by C minus C alpha E. So this is what basically this will be. So this is how you determine the proportion of different phases in below and above eutectic temperature in the eutectic mixture as well as in the liquid phase. So we will do further analysis of phase diagrams in the next lecture. Thank you very much.